Greetings, everyone. Now let's talk about solving logarithmic equations. Equations that already have a logarithm in them, and this time you want to get rid of the log instead of using logs like in the last video. Okay, so equations like log base 6 of x equals 3. What I'm going to use is that inverse property between exponentials and logarithms that we had, where if I have a logarithm as an exponent, as long as these two bases match, they're inverse operations, and you're just left with that argument x still standing as the only thing left. Okay, so how do I use that to my advantage? Well, I call it crank up the music. In other words, raise the bass. So right here what happens is I'm going to bring up a base 6 on both sides. What do I really mean, bring up a base? It's sort of like a visual for you. It's not really moving. It's not like bringing anywhere. What I'm doing is I'm saying I want to use both sides of the equation as exponents in the base 6 to that power setup. Okay, so what that becomes is 6 raised to the log base 6 of x is equal to 6 to the 3. Okay? Then, since these two are the same base, I am just left with x equals 6 to the 3 power. So therefore x would have to be 216. Okay? So that's the basic idea of what we want to do to get rid of a logarithm. I'm just going to use it as an exponent, which, remember, that's what logarithms do. They calculate exponents. So in this case, I'm saying, okay, put your money where your mouth is, use yourself as an exponent, and then this is what happens. Okay, so let's look at this example now. 2 times the natural log of the quantity 5x minus 4 equals 6. I have a couple of options here. I could use that logarithm property where I bring a number inside as a power, but notice that'll make the equation more complicated. It'll square my x. I don't want to do that. Instead, I'm going to just divide both sides by 2. Since the other side is just a number, I could easily get away with that. So what I'm left with is ln 5x minus 4 equals 3. Now I'm in the same situation as I was over here. You just need to remember that ln is an abbreviation. It's just shorthand for log with an e base. The number e, right? The natural number is the base here. So what I'm going to do now is I'm going to raise the base. What base? I'm going to match it. I'm going to use base e as a base. So then this is e to the ln 5x minus 4 power, and this is e to the 3 power. Well, lovely. Now these two have the same base. Remember, this is base e also. So these are going to go away. So what does that leave me with? I have 5x minus 4 is equal to e to the 3rd power. Now, of course, e to the 3 is an irrational number. I'm just going to leave it like that for now until the very end, and then I can punch it in and get a number for it. But it's a linear equation now. I just need to get x by itself. So I'll add 4. Like so. And then I'm going to divide by 5. So x is equal to e cubed plus 4 all over 5. And at this point, I'll go ahead and punch it up to see what the actual numerical value of that is, approximately. Right? Since it's irrational, that's all we can do is approximate it. Don't forget to keep your numerator in its own parentheses if you're going to type this all in at once. So I have e to the 3 plus 4, and then I'm going to divide that by 5. So I get 4.8171. All right, first actual application. Find an x-intercept for a logarithmic function, right? Well, remember this is just a log base 5 of x function, which has the asymptote on the y-axis, right? The vertical asymptote, and it just hooks out to the right. But it's been shifted left 2 and up 1, right? It's been shifted left 2. So negative 2 should be my vertical asymptote there, right? And it's been shifted up 1 also. So my new center is there. And let me just draw in the shape. Something like that, right? Okay. So if my graph is somewhat accurate, we're expecting something in between negative 1 and negative 2 there. All right. X-intercept is whenever y is 0. So I'm going to be solving this equation. 0 equals 1 plus the log base 5 of x plus 2. Okay. So I want to get rid of this logarithm, but remember to do that, I've got to have the log by itself on one side. So I'm going to subtract the 1. And let me rearrange it the other way, just to make it more like what we've been seeing. The log base 5 of x plus 2 is then equal to negative 1, because I'm subtracting the 1 over, right? And then I flip-flop the sides. Okay, so now I have this logarithm that I want to get rid of. Just like before, I'm going to raise the base, right? Start dancing. Base 5 with the log base 5, and then over here, base 5 again. So these are going to go away. Don't forget, this is an exponential thing. This is not 5 times negative 1. This is 5 raised to the negative 1 power. So I have x plus 2 is equal to 5 to the negative 1 is just 1/5, right? 5 to the 1 is 5. The negative moves it to the bottom. Okay, one step left. I just need to subtract 2 from both sides so that I can get my x value, right? And here in this one, I can actually get an exact value. 1/5 minus 2, 2 is 10/5. I'm getting negative 9/5, right? So I can actually keep it like that. Now, of course, negative 9/5 is negative 1.8, which, as we said, it's somewhere in between the negative 1 and the negative 2 there, right? It's still hugging the asymptote really close to there is what's happening.
So here's a better look at the graph that we were just talking about, right? It's the 1 plus log base 5 of x plus 2. It has a vertical asymptote at x equals negative 2, as we said before. There is the center point at negative 1, 1. And then, of course, the intercept that we calculated, negative 1.8, is the same thing as negative 9/5.
Let's do 2 more examples of solving logarithmic equations, and this time let's have more logarithms in the mix. Okay? Anytime you have more than one logarithm in an equation, your best bet is to get all of those logarithms on the same side, because we have all those nice log properties that allow us to mash logarithms together into one single logarithm, right? So what I can do then is treat it like one of the logarithm equations before. Once I get it mashed into a single, I can just do the base thing on both sides. Okay, so here, I have a logarithm on the left, I have a logarithm on the right, and what I really want to do is get those logarithms together. So I'm going to subtract. So that this goes away, right? Okay. So then I'm left with the log of 3x minus 5 minus the log of 19 minus x equals 1. right? They are the same base. Don't forget, LOG with no base is base 10. They are the same. So I could just mash these two together. And remember, subtraction just leads to division. So I've got the log of 3x minus 5 divided by 19 minus x. Okay, well now I've just got that logarithm equals number set up again, right? What I need to do is raise a base on both sides. This is base 10, right? That's understood. So I'll be putting a base 10 on both sides. Okay, now remember, this is base, not just multiplication. Okay, so of course these two are inverses. And I'm left with 3x minus 5 divided by 19 minus x equals 10 to the 1 power is 10. And now I've got a rational equation I need to solve. So I'm just going to multiply by this denominator to both sides. I'm going to distribute. Right? Linear equation. I'm going to add 10x and I'm going to add 5. Okay? So what does that leave me with? I have 13x is now equal to 195, right? So I just divide both sides by 13, and I'll get that x is equal to 195 over 13. Now let's see, does that reduce? 195 is going to be 5 times 39, right? And 39 has a 13 in it. Sure enough. Right? So 13 into 39 leaves 3. So then my x is, what, 15. You always want to double check a logarithmic equation. Okay? I'm going to check it by plugging it back in. And really, the decimal that you get from doing the logarithm is not what we're looking for. What I'm really looking for is to make sure that it just can be done. Because remember, you can't do a logarithm of a negative output or a negative input to the logarithm, okay? That doesn't mean if something comes up negative, it's automatically bad. It just means always check, right? Just like square root equations. If you have a logarithmic equation, you really want to always check, okay? Especially when it's the higher level ones like this. So I'm gonna take the 15 here, and I'm gonna plug it in. So I've got 3 times 15 is 45, minus 5 is 40, right? And log of 40 works, right? 1.6. Over here, I've got log of 19 minus 15, which is really just log 4. So 1 plus log 4. Still also 1.6, right? So it does work. It is good, a good solution there. Okay. All right, so another application. Find the intersection, right? Let's say I have these two logarithmic graphs. I'm going to end up solving the equation where they're equal to each other, right? So I'll be solving 2 minus log base 4 of x is equal to the log base 4 of x plus 8. Now real quick, let's look at the graphs of these guys, right? The top one here is just log base 4 of x. It's been vertically reflected, right? Up and down reflected, and it's been shifted up by 2. So it still has the asymptote on the axis here, but it's been flipped. So instead of hooking up and right, it's going to hook down and right like this. And the vertical asymptote is still the axis there. So we're looking at something like this, right? Something like that. Call that G. Now H is just your plain ordinary log base 4 of x, but it's been shifted 8 to the left. So we're looking at something where negative 8, right, is my vertical asymptote, and it's going to do something like this, like that. Now it could be a little bit off, but since this thing doesn't go on that side, it is going to be positive, okay? And they do intersect, so we are looking for, you know, an actual answer here, and just one to be sure. Because sometimes logarithm functions can, you know, flip around and hit each other twice, and sometimes they can miss each other altogether. So it is possible to get several different types of answers here. These two should have just one intersection. Let's find it. So like before, I've got more than one logarithm in my equation. So I want to get those logarithms together on the same side. I'm going to add log base 4 of x to get it over there. So I have 2 equals log base 4 of x plus log base 4 of x plus 8. All right. I want to have a single logarithm. So I'm going to bring these two logarithms together and they're added, which means I'm going to multiply this time. I have x times x plus 8, right? But what's x times x plus 8, honestly? Couldn't we just make this easier on ourselves? X squared plus 8x, right? Okay, so I have a number on one side and a logarithm on the other. I'm going to use that raise the base property again. What's the base? Base is 4, so I'm going to use a 4 base for both of those exponents. And then, of course, these two are going to go away. 4 squared is 16. Like so. And then I'm going to subtract the 16 because this is a quadratic. So I have x squared plus 8x minus 16 equals 0. I saw that it was a quadratic immediately, and so I just got everything to one side equal to 0 because I'm either going to factor or formula, right? Now factoring probably is out of the question. Two things that multiply to negative 16. I don't think we're going to find nice ones that add to 8, right? 4 times negative 4 wouldn't work. So let's see. Since I have this quadratic and I can't factor, well, I guess I got to do the formula, right? Okay, so let's do that. Let's set up our quadratic formula here. Let me rewrite the equation. Plus 8x minus 16. So x equals negative 8 plus minus square root 8 squared minus 4, 1, negative 16, all over 2 times 1. Alrighty. So I have x is equal to negative 8 plus or minus the square root of, now 8 squared is 64, 4 times 16 is also 64, but look, negative times negative, it's positive. So 64 plus 64, that's 128 all over 2. I can simplify that square root of 128, right? 128 is 64 times 2. Right? So that's negative 8 plus or minus square root of 64, square root of 2, right? 64 times 2 is 128, and the square root of the 64 is 8. All right, so lastly, I've got 8 over 2 and 8 over 2, so that's negative 4 plus or minus 4 square root of 2. Well, that's giving us two solutions. And just from what we know of the graphs, I'm only supposed to be getting one, right? Well, remember what I said over here, especially in the more complicated ones, you should go back and check and make sure that things work out. If I do the -4 with the minus, that's a guaranteed negative number. That doesn't mean it's bad. However, this x right here in this function is not added or subtracted with anything. If I take a negative number and plug it in, it would be the logarithm of a negative number, which would automatically make it no good. Okay, here, this is what I'm saying. The two values that we have here, right, is this or this, if you separate it out. This one right here is a guaranteed negative number because of the way I'm adding two negative numbers here. And that top function can't handle that. It's out of the domain. So that's not a good solution, right? -4 plus 4 square root of 2. Let's go ahead and crunch up what that is. -4 plus 4 square root of 2. 1.657-ish. Okay? And if you plug that back in, you'll find that it does work. Right? In fact, we do want to plug that back in, right? Because we're finding the intersection point. So I need an x value and a y value, right? So my intersection point there equals 1 point, and we'll do approximate, 1.657 comma. Now I'm going to take this as my previous answer, right, in the calculator, and I'm just going to plug it in. Don't forget, I have to actually convert that, right? That's going to be the log of the number divided by the log of 4, okay? So in my calculator here, let me write out what I'm going to put in the calculator here. I'm going to do 2 minus ln of previous answer divided by ln of 4. That's how I'm going to get my y value for the intersection. Okay? So here we go. Make sure the previous answer is in fact the one, that should be the correct answer for x. And then I'm going to hit 2 minus ln previous answer divide by ln 4. I get 1.6357. Ooh, really close, right? 7 technically, so I guess that could be an 8. Okay. Well, I hope this helps you with all of your logarithmic solving endeavors.
So here's a better look at the two graphs that we were just calculating the intersection of. 2 minus log base 4 of x and log base 4 of x plus 8. Notice they have different vertical asymptotes. G has the vertical asymptote at 0, or the y-axis, and H has the vertical asymptote at -8. Their corresponding center points, right? The intersection point here, where they do actually meet, being the 1.6569 and the 1.6358, same as we calculated.